Today we're going to look at doing some work on yield. You've seen those where they say, if I give you this and that, what do I get out? Then where they say how much yield. Now remember, in a circumstance like that, essentially the chemical that we've got may not be pure, right? If they tell you it's pure, obviously then there's no contaminants in it. So the yield that you get out will match the theoretical yield that you should get out, as near as darn it anyway. What we've got here is we've got, and you've seen the question, but let's recap. Nitrogen and hydrogen are reacted to synthesize ammonia in the Haber process. If we are given a yield of 72%, which equated to 5.35 kilograms of ammonia, calculate the mass of nitrogen and hydrogen that was reacted. Okay? Well, first of all, obviously we start with the balanced equation, don't we? That's always our starting point, because that's the recipe. That's what we're going to be using to do it. Okay, so let's have a look. Let's write down the reaction, and we've got N2 gas plus H2 gas. Okay, going to NH3 gas over there, and we've got, to balance it, we've got nitrogens. Remember, 2 nitrogens over there, and we've got our three hydrogens over there to do that, right? So our ratio, let's write down the ratio over here. The ratio is going to be equal to 1 as to 3 as to 2. Okay, that we've got. Let's see, what are we given? Given in this case, they've told us that we've got 5.35 kilograms of ammonia. So let's have a look. Given 5.35 kilograms, which is 5350 grams over there. Okay? And they've told us that that's the actual yield. So we've got that is actual yield. Right? That's where we're going to start. And they've asked us, required to find how much of these guys reacted to give us that. Okay? First of all, what do? Molar mass, always, right? Molar mass, 28 grams per mole there. Molar mass over here is going to be 2 grams per mole. And over here, 17 grams per mole. Okay, and remember, just an aside, we can't just add the masses, can we? Nope, because the law of conservation of mass comes after we've applied the recipe, the number of moles that we're going to be using. So let's have a look here then and see what we've got. All right, so now remember that what we've got is that the actual yield, right? Now therefore, let's work out what the theoretical yield would be. Theoretical yield. Okay, over here is going to be equal to 7340.55. 7340.55. Let's see what we've got. Let's just go down here. Percentage yield, okay, is always defined as actual yield, okay, over theoretical yield. Right? Okay. So in this case, we can say that our theoretical, right, because we've been given actual and percentage, then we've got our theoretical yield is going to be equal to the actual yield, okay, is 5350 divided by 0.72, which is where we get the 7430.55, and you just 7430.55 grams, right? So what have we got here? We've said, right, therefore now we know that that is the theoretical yield of the substance that we've got, right? So now let's work it backwards, shall we? If we've got this, we can take it straight back and we say, right, number of moles. Number of moles over here, we're going to divide by 17, which is going to give us 437.1 moles. And if we take this back, all right, in the ratio 1:3:2, in other words, divide by 2, okay, which is then going to give us 218.55. If we divide, which is 437.1 over 2, and 655.64 moles, in other words, this is going to be equal to 437.1 divided by 2 multiplied by 3 to preserve the ratio. And then we can go back up with that, and we can now calculate at the top. I'll put it into red. Let's remove the question marks because we're going to calculate them. We've now got so many moles times that, which gives us 1311.28 grams. And of the nitrogen, it gives us 218.55 times 28, 6199. Oh, sorry, my bad, sorry. 6119.4 grams. Right? That's what we've got for that. So let's just go through it. We've got nitrogen, hydrogen. They've given us an actual yield, okay, that we got out. All right. Then we can work out from there the theoretical yield. Then we can take that back to work out what we actually started with. Just based on the formula that percentage yield is going to be the actual yield divided by the theoretical yield. Okay. The theoretical yield obviously is if it's pure, isn't it? If you look at this, let me just see. Yeah. If you look at it, and there's one later that I'm going to do where I'm going to show you, but essentially we've got a chunk of material. Let's say it's this material here, and what we're doing is we're saying that of you, that much is the pure stuff. The rest is not pure. It's impurities. All right. I'll explain again in a later one. All right. Let us now have a look at a different one. They say 1 kilogram of iron oxide decomposes. All right, decomposition reaction. All right, and they've told us 1 kilogram of iron oxide decomposes according to the following reaction. And here they give us 2 Fe2O3 as a solid, okay, going to 4 Fe solid plus 3O2 gas. Okay. Now, what they say to us here, if we end up with 600 grams, let's find out. Okay. Whoops. Let me put in my ratio first. Okay. Let's put in the ratio over here. This is 2, giving us 4 and 3. All right. Let's draw a line under that, and let's put in what we are given. And what we're given is we end up with 600 grams of solid iron. Okay. Calculate the percentage, and they've told us that we started off with 1 kilogram, which is 1,000 grams. We always put them to grams. Okay. So let's now go forward. First thing we've got to do is we're going to say to ourselves, okay, I've just done them up ahead, just so we can go through them quicker. All right, what we've got, let's look at the molar mass, right? The molar mass over here is going to be 2 times 56, which is our iron, plus 3 times 16, okay, which is our oxygen, right? 3 times 16, that ends up with 160. Per mole, and on the other side it's 56 grams per mole. Okay, well, so far so good. Let's just draw that line down there. So what can we say? Let's have a look here. We say, okay, molar mass, okay, number of moles. Well, the number of moles over here is 1,000, which is what we started with, divided by 160, which is equal to 6.25 moles, right? Now we say to ourselves, this should give what? It should give, right, the 6.25. We've now got to put it into the ratio of the iron, okay? So therefore, we're going to 2 as to 2, right? Or 2 as to 4, rather. So what should we get? We should get on the other side here 2 times 6.25, right? Because there is 2 moles, and that must be 4, which is double, right? So we're going to get 12.5 moles. All right? Well, therefore, we should get how many grams? 12.5 times 56. We should got 700 grams, okay? But we didn't. We only got 600 grams, didn't we? Therefore, right, it means that we say the percentage yield, okay, is going to be equal to actual. We got 600 in this case, 600 grams over theoretical, which is 700 grams, which should give us 85.71, okay, percent. Okay. Remember, you can also use, you've used mass there, we could have put moles over moles, okay, in other words, actual over theoretical. We could also have said actual volume over theoretical volume, right? Would have given us the same issue. So in this case, what we've got is there's 2 where we've had theoretical and actuals, right? And obviously they can put the question the opposite way round. They can say we started with this, we ended with that, or we ended with that, and what did we start with, given percentages. The process is still the same, isn't it? We're just looking for the theoretical yield and the actual yield. Let's just have a look at this that we said here. We said that on this one, we said we started off with 1 kilo, right? Okay. 1 kilogram of it, or 1,000 grams. We should have got, okay, out of that reaction, we should have got 700 grams, right? If it was all pure. But we didn't. We only got 600 grams. So do you see what has happened here? We've had a kilo. If it was pure, we should have got a total of 700 grams. In other words, of that, right, the rest was the O2, wasn't it? Okay. We should have had over here, let's go back to the green. This here, if it was 100%, that would have been the O2, right? The balance would have been the O2, if it had all been pure. But we only got 600 grams out, which means it's not pure. There's an element of impurity inside it. Let's just have a look at the next question then, all right? The next one is a question. Let's just go back. And we say, a handful of seashells weighing 7 grams are collected and mixed with concentrated HCl according to the following reaction, right? Now, you know that seashells are basically calcium carbonate. So we say here, CaCO3 solid plus HCl aqueous is going to go to, and what we're going to give it is we're going to go to CaCl2 aqueous plus CO2 gas plus H2O. And we balance it. They've told us how to. We just put a 2 over there. Okay? So now we say, okay, what is our ratio? Is 1 plus 2 goes to 1 plus 1 plus 1, like that. Okay. So, now, at the end of the reaction, we collect the CO2 and find that at STP it occupies a volume of 1.15 liters. So we collect the CO2. This is going to be our given, isn't it? Given, we say 1.15 liters at STP. Hold on. Right, now this is where we stop and we say, hang on. Normally we used to be given grams, but we've been given a volume and the words STP. STP means straight away it's got something to do with 1 mole equals 22.4 decimeters cubed at STP. All right? Straight away. That's where we go. So let's apply that and work out from there. All right? And they want to know what is the percentage purity, and they want to know percentage purity over there. All right? So let's have a look. Okay? And we're given 7 grams of that. Okay? So obviously 7 grams of this is going to decompose according to if it was pure, a theoretical amount it would give us, and we've got a practical amount that we've actually been achieved. That's what we measured. So let's have a look at this. Okay? The 1.15. That is 1.15 cubic decimeters, isn't it? Okay? Because 1 liter is 1 decimeter cubed at STP. Now, I'm just going to put here my molar mass. And the molar mass of calcium carbonate is 40 plus 12 plus 3 times 16, which gives us 100 grams per mole of the molar mass, right? Okay, and let's now work out number of moles. Number of moles, okay, using the 1.15, let's go through it. Well, okay, 1.15, how many moles? We know 1 mole. Just that guy out. This is 22.4 decimeters cubed is 1 mole. Therefore, how many moles is that? Okay, it's 0.0513. Okay, 0.0513 moles, right? Can you see that? Okay. Whoops. So let's have a look. We say, right, it's 1.15, okay, divided by 22.4. Can you see that? It's 1.15 over 22.4 gives us moles, right? Which is that figure over there. Right, now let's move along. Right, so once we've got moles, what can we do? We can now apply the recipe. And we say 1, in this case, goes to 1. Okay, 1 is to 1, isn't it? So therefore it should be 0.0513 moles of CaCO3. That's what we should be getting out of this reaction. Okay, let's have a look. Therefore, we can say, okay, this 0.0513 over here requires, okay, in other words, let's just think. We got the 1.15, all right? Now we apply the moles and we say, right, that should have come from how many grams, okay? In other words, how many grams of CaCO3 had to decompose, assuming it was all 100% pure. So we say it's 0.0513 times 100 is going to be equal to 5.13 grams. So what are we saying? We're saying that 5.13 grams of CaCO3 in the original mixture would have given us that. Let's just take a quick look at it. All right? So we say, all right, okay, this is 5.13 grams over there. That yields 1.15 decimeters cubed at STP, correct? That's what we've been told. That's what we got. When we did the decomposition, we actually ended up with this. So, but hang on, we had 7 grams of this material. We had 7 grams of the material. What does that say to us? It says, well, it says quite obviously then that you only needed 5.13, so there was only 5.13 grams inside that. So therefore, the percentage purity is going to be equal to, let's have a look, it's 5.13 divided by 7, and as a percentage, that's going to be equal to 73.3. Okay? And obviously, what we can say, last of all, is therefore, this little bit on top here, that is 1.87 grams, I think, grams, did not react. Okay? So, therefore, what we're saying is that of that chunk of material, in order to get that gas, right, we only needed 5.13 grams of calcium carbonate. The rest was actually impurity. We didn't need it. Okay? Okay, let's have a look now and have a look at the last one in this series. If 1 gram of magnesium reacts with 85 centimeters cubed of HCl of a concentration, what volume of hydrogen will produce at STP? Okay. Right, once again, what do? We start off with a balanced reaction. Okay. Let us write down the balanced reaction for this one. They've said magnesium plus HCl. Okay, let me just get it back to my plus HCl aqueous. Okay, and what is this going to give us? This here is going to give us HCl aqueous. And what do we get? We've got a metal plus an acid gives us a metal salt, right? Magnesium chloride plus hydrogen gas. Correct? Everybody should be happy with that at this stage of the game. Okay. Now we have to balance, but the MgCl. Cl has got a valency of -1, magnesium plus 2. Therefore, we need a 2 over there. To balance that, we've got that. And there we go. She's balanced. So let's have a look at the ratio here. The ratio is 1 mole to 2 moles gives me 1 mole plus 1 mole. Correct? Now we put down given. Okay, we're given 1 gram. All right? And we're given a volume, 95 centimeters cubed of acid. Okay? Let's have a look at the molar mass. Molar mass over here, 24 grams per mole. Right? It's 24 grams per mole. All right? And 36.5. 30.5 grams per mole. And then number of moles is N. In this case, we've got concentration, which is N over V. Concentration over here has been given. In this case, it is 0.5, if I'm not mistaken. It's a concentration of 0.5, yes. 0.5 moles per cubic decimeter. Okay, so this 95 centimeters cubed. We don't work in centimeters cubed, we've got to change that, right? Centimeters cubed, we're going up 1 step. Up means we divide. Okay, 1 step. We're going to divide by 1,000, so that's going to be 0.095 decimeters cubed, right? Now, therefore, can we work out the number of moles of HCl? Yes, we can. We know the concentration, which is equal to, just let me write it, N over V. We know V, don't we, guys? V is 0.095. So it's 0.5 times 0.095, right? And that should give us then 0.045. .045 moles. And then we can now say, right, but they've given us two substances. Remember always, when two substances are given, look for limiting reactant, because sure as eggs, it's in here somewhere. So otherwise they'd have said in excess, or they'd have asked us to calculate how much is necessary, wouldn't they? So let's have a look here. How many moles? We've got 24 grams, okay, per mole, and will give us 1 gram. So that's going to be, let's just check, 1 is 0.0417, 0.0417 moles. Now, let's take this up like that. Right, let's take this up. Now, what's the next step? The next step is to have a look and say, whoa, 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 whoa. We need to stop at this point and take a breath, because we've been given here 0.0417, 0.045, right? So I always like to say, right, 0.0417 needs how many moles of that? Let's just check our ratio is 1:2, all right? It needs 1:2. So I've got to double that, correct? 0.0417 times 2 is going to be 0.0833 moles. Then I go backwards the opposite way, and I start off with my 0.045 moles, okay? Needs how much? And 2 to 1, which means it needs half, 0.0225. Okay? And tick. We have enough to do it, right? Because we've got, that's the number I'm comparing, there to there, 0.0417, 0.0225. That's how much we need. Let's have a look at the green side, okay? On the green, 0.0417 moles, right? That's what we've got. I need to react double that, 0.08. I don't have it. I've only got 0.045. So, not enough of the acid. Let me just check, make sure that I've got the acid. Yeah, not enough of the acid there, right? Then what do? We now continue, okay, as normal, and I'll just do it just for fun in the blue. So we say, right, then we go 0.0225 reacts with 0.045 moles, all right, like so. In other words, that is used. This is then used, and it synthesizes or gives us, and it's in the ratio 2:1:1:1. So therefore it gives us how much hydrogen at STP? 0.0225 moles. Remember, 1 to 1. There's our ratios, right? So therefore we've got 0.0225 moles, and they've asked us at STP. So just to complete it, yep, STP means we're going to use the 22.4. 1 mole equals 22.4 decimeters cubed. Therefore, 0.0225 must be equal to how much? And you multiply it out, and it becomes 0.54 decimeters cubed. Let's have a look at on this side. I just want to change back now. Let's have a look. So let's put in here start. Well, hang on. How much did we start with? 0.0417, didn't we? 0.0417 moles, right? And how much of the other guy did we start with? 0.045. And let's do a little technique here. Used 0.0225 and 0.045. Remember, that was the times 2 that we did. So therefore, left over is going to be 0 of that, and on this side 0.0192 moles. Just subtract that one from there to give us 0.0192 moles, and therefore this one was our limiting, wasn't it? Limiting reactant, because that's the one that's been used up. And if they said how many grams, it's 0.0192, all right, 0.0192 times 24, 0.0192 times 0.0192 times 24 is 0.461 grams. 0.461 grams left over. Okay. So there we've looked at a few of the yield questions, one with a limiting reactant question, and I hope that you can see that they all follow exactly the same recipe. Fundamentally, I know that was a very long calculation session, but they all follow exactly the same recipe. You put down what you're given, and you work it to moles, and you express it backwards or forwards using the ratios in terms of moles. Thanks for watching those, and hopefully you'll go through those again and again, because once you've got the hang of the process, very straightforward to do these calcs. Cheers, have a good one.